Probably it's time to start the second session of this lecture. Okay, so let's consider this situation. This is the schematic of the experimental measurement we learned in the previous lecture slide. Now assume this is 50 ohm and this is 500 ohm. This is the resistance or impedance seen by this direction, which was G1 in the previous discussions. And this is the G2, okay, which is seen by this direction at the injection point. And this is the 5 ohm, this is the 50 ohm, 500 ohm. So ratio between this is 0.1 or 10 times. And we are measuring this pseudo loop gain, all right? And this RS. RS is source resistance of this AC injection circuit, which is 40 ohm, but this one is totally independent of our assessment of this pseudo loop gain. Okay, so there is the first one, and the ratio between this G1 and the G2 or R1 and R2 is given by this in terms of dB. This is minus 20 dB. So this is the minus 20 dB line representing this ratio between G2 and the G1. It's shown here. And this T is true loop gain. We assume the equation of this true loop gain is known for the educational purpose. So you want to compare this one, this true loop gain and the pseudo loop gain we will be measuring using the asymptotic analysis discussed in the previous slide. Okay, and this blue line is the result of this asymptotic analysis of the loop gain expression given by this. Okay, this is the equation, the fundamental equation we're going to use. This relate between the true loop gain and pseudo loop gain in terms of the ratio of these two impedances, and this one is not appearing here. So this can be any number. This 40 ohm is the reasonable number for this. And based on this magnitude difference, maybe it is a good idea to divide this frequency range for the evaluation into two regions. This is the region A. Before this line, this is called the region A. Region A. And the right hand side of this Bode line, region B. Okay, all right. So in region A, we consider this part first. Then this fact first. This is true. Magnitude of G2 is larger than G1 by 10 times. So you can be, this is large difference. Then maybe we ignore this. We ignore this. Okay. Then the remaining is, this is ignored. This is equation 1. Ignored by equation 1. Then remaining part is T prime S, which is the pseudo loop gain, is T, which is the true loop gain, plus G1 divided by G2. Okay, this is our first approximation. And in this region, the magnitude of the loop gain, both the true loop gain and the pseudo loop gain, magnitude of them is much larger than this minus 20 dB line. So this can be also ignored. So we ignore this, and with this condition, then, okay, let me write down this by number 2, equation number 2. Then T prime is similar or almost the same as T, which indicates the pseudo loop gain is almost the same as this true loop gain. So this is valid for the region A. Okay. Region B, this is true, right? This is the true regardless of frequency range. Then still you have this approximation. So in this region, T prime is T, this is a true loop gain, and plus G1 divided by G2, and the magnitude is considered. This equation remains the same, but in this region, if you compare magnitude of the T here and the ratio of two impedance, this one is much larger. This term is over this one. Then in this region, this T prime is actually this one, G1 divided by G2, okay? Maybe magnitude of this, all right? So this blue line indicate at this frequencies, this is same as, this is the pseudo loop gain, is almost the same as the true loop gain, but after this Bode line, it follows this line. So in this region, there is a huge difference between true loop gain and the pseudo loop gain, okay? But it won't happen in practice because the ratio of between this one and this one is only 0.1, okay? In practice, this will be maybe 0.01 or 0.001, something like that. Actually, this input impedance is much larger than this. Still, maybe this one is okay, but this will be larger than this one by 10 times or 100 times. Then this behavior, this phenomenon occurs at very low frequencies. So in your frequency range of interest, it follows this one, okay? And it happens at here, so you don't care about this, okay? So this is okay, all right? Still, this one is okay, but theoretically, this will happen in this case because the difference between two resistance are not that big, okay? All right. Suppose you want some refinement of your estimation, then maybe you still ignore this and you can keep this, okay? Maybe you keep this for some reason, then you calculate this because difference between 1 and 0.1 is not that big, that maybe you want to keep this and use that as the correction factor. Then this is the calculation in dB. So this is the 0.83 dB, all right? So pseudo loop gain will be raised by this much, okay? This is also error, some additional error, but this is this is refinement, okay? Based on this relationship, all right? Then so this distance between this black and blue line is this one, 0.82 dB, okay? If you need further refinement, okay, then maybe you connect these lines smoothly like this, something like this, and something like this. So the deviation between two curves is 30 dB and 30 dB, okay? This won't be necessary, but this is possible. So you think this is the very close estimation of true loop gain, but there is just some inherent error between this and between this, okay? But still, this explains the principle of evaluation or prediction of pseudo loop gain using this setup. This one strange thing is this resistance has only 10 times difference. If the difference is 100 times, 1,000 times, then this pseudo loop gain will be very close to the true loop gain. Okay, so this is the first one. And the next slide explains the measurement of unstable loop gain. Assume this system, okay, a combination of the block 1 and block 2 and this feedback circuit HS is initially unstable, so there is no way of measuring loop gain of unstable system because the growing oscillation will happen in the system. It's impossible to measure anything, okay? The only way is somehow you stabilize this system and you consider the additional factor that stabilize the system. Okay, all right. So this is the situation. So this is initially unstable, and you insert the reasonably high Rext. This resistance will combine with this GS. Okay, so this one plus this one can be considered as the composite source impedance. If you remember the previous discussions, this source impedance is totally independent of the evaluation of this pseudo loop gain. Okay, so presence of this, still you can measure the exact transfer function from here to there, regardless of presence or magnitude of this. This is the pseudo loop gain. Okay, but original system was unstable. But by adding this Rext will stabilize this originally unstable and also unstable system. Okay, the feedback signal is somehow divided by this one and this one. So there is just some attenuation in magnitude. So with reduced feedback gain, effective feedback gain, the system will be, the total system will be stabilized until from here, until if you take a look at this, the system is unstable, but this external element is stabilizing the overall system. So at that situation, still you measure this and this, okay? The ratio of between two, there is the loop gain of unstable original system, and the loop gain measurement result will say the system is unstable because maybe the gain margin is positive, something like that. So we reduced using this with this resistance, externally reduced the feedback gain to stabilize this. Then we measure the characteristic between this and this, which is correct information about this unstable system, and the loop gain will say the system is unstable. Okay, so if you have unstable system, you are very eager to know or to measure the loop gain because you want to find out the origin of instability and to fix it. Okay. For that purpose, if you reduce the gain, feedback gain, somewhere here, then the system will be stabilized. That information is available from this experiment. Okay, so this is the original equation, and there is no dependency between this equation and this value. Okay, I wrote down this one. Additional resistance Rext is totally irrelevant to the TS evaluation, and reasonably large Rext will effectively reduce the feedback gain by this voltage division, and that will stabilize the system, still yielding, if you measure ratio between this and this, that information is still correct information about the system without considering this. Okay, which is loop gain of unstable system. Of course, the loop gain measurement will say that system is unstable. Okay, but if you use too large Rext here, then the DC information will be excessively attenuated and the bias point will be perturbed. Okay, to avoid that, you may add very large inductance here. So AC feedback signal will pass through this and attenuate as desired, and DC component of this signal will pass this, and it won't disturb the operating point that much. Okay, that will stabilize the operating point and also stabilize this AC feedback reduction will stabilize the AC feedback loop, and that allows us to measure this loop gain. Okay, all right. This technique is useful for some case, and maybe it will be difficult for some special case because we are only fixing this magnitude of feedback gain externally. If there is something in the phase, this one works. Okay, at that case you may add some phase boost using some OPM, something like that. Right, there is the additional alternative. Okay, but basic idea is this one. Okay, this measurement is valid even the unstable system case with this example. Okay. So far we discussed the everything, most thing about the experimental measurement of the loop gain. And the remaining part is about the computational method. So PSIM and other software like Simplis, but PSIM is very good because there is a free copy. Okay, student version, license-free copy. Okay. So PSIM has this functional block. So there is no transformer. So this is the program. They can do whatever they want to do. Okay, because just program. So here this VT is added some I don't know here, and there is a voltmeter. This is measuring only AC component between here and there. Okay, then this VAC is magnitude is Vx hat in dB minus Vy prime dB. Okay, so this is minus. Okay, we have minus here. So this plus minus, meaning of this plus minus sign is this is positive, this is negative. Then we have this, and Vy prime is defined in reverse polarity with this. So minus is coming out here, and this Vy prime is this one, and you have this. Okay, then this is Vy hat divided by Vx hat. This is what? This is loop gain. Very close to true loop gain. Okay, it's not exactly true loop gain. True loop gain. The loading effect will be considered, but because usually the impedance, input impedance of this thing is much larger than output impedance of this converter, that impedance, voltage division ratio is going to be 1, very close to the unity. Then what you are measuring is very close to the true loop gain. Okay, so ratio is okay, but what you are measuring is here Vy minus Vx. Okay, then you need minus sign of this. This is the input, this is the output. So output minus input minus output, right? So you have minus sign here. So the way of doing this is just simulate this and just put minus sign, minus 180-degree phase delay addition to the result. That is automatically done in the software program or measurement program. So what you are seeing is negative of this. Okay, so you just take a look at this here. Then when phase is minus 180-degree, okay, so this is the loop gain crossover frequency. So amplitude of ratio of the two signals becomes unity. Okay, and the phase is way above this one. So this converter is very stable. Okay, but if you introduce some phase delay, all of the frequency range, and this curve will be shifted like this, something like this. No. Something like this. Okay. And this becomes minus 180 at this frequency. This magnitude is 1. Okay. That becomes at that frequency where the phase becomes minus 180-degree, ratio between input and output is 1. That means what? There is the condition for the sustained oscillation. So there is the borderline between stability and instability. So this is considered as the margin, phase margin PM. Okay, we discussed this before. Okay, it's same idea here, same thing, right? So loop gain simulation. I control this. Not carefully, systematically selected this to have a phase margin of 60 degree. So this at this frequency, the distance between this and this minus 180 degree is 65 degree. So this is one case. Okay. So you have this type of parameters for your 3-pole 2-0 compensation, and I have another that comes later. Right? So this is an example. Right? This is example. The same example. Okay. I intended to specify the phase margin here, like this. Okay. Same plot. It really doesn't matter. Okay. Let me explain this. Okay. What I have drawn here is what. Okay. So we went through this, right? So this is the magnitude of loop gain, which is very close to the true loop gain, and this is a phase of loop gain with additional minus 1. Okay, there is some error because of this position of these two signals. So you should add minus 180 degree, then you will get this. Okay, and this equipment is the waveform capture. Okay, so this simulator, this is another equipment. This simulator is capturing this, and inside of the PCM, it removes this noise component and remove this DC component, and using this, it generates this plot. Okay, so waveform capture. They are not measuring, just capturing some with something. Okay. Okay, so wow. I intended to take a break somewhere. Okay. All right. And it's about this graphical representation of frequency response. We already practiced the Bode plot a lot, and there is another plot. So this is a Bode plot, and this is the polar plot. Okay, the same information is displayed in different format. Okay, in Bode plot, this omega as frequency is explicitly shown here. Okay, and this is the magnitude. X-axis is magnitude in dB scale, and you have another axis for the frequency, or you share with this for 2 plus, but you can use separate frequency axis, and this is the phase. Okay, this is a Bode plot. This is very good one, and another plot is called the polar plot. Okay, this is S-plane, and this is the real part of this something Tm loop gain. Okay, so this is imaginary axis and the real axis. So of course this is the complex number having magnitude and phase. So Tm is this one, magnitude and phase Tm. Then this will be transferred to real part. This is nothing. Like this, okay? Can be separated, real part and imaginary part, and with this is plot to add some trace like this. Okay, take a look at this part at low frequencies. Okay, at low frequency magnitude very large and phase is minus 90. That means this plot start way down there. Okay, but let's assume it start here. Actually, it becomes larger and larger. So it goes here, and at low frequency phase is minus 90. So it is on this negative imaginary axis. Okay, and the phase becomes more negative in this region. Then this will travel in, this is the first quadrant, second quadrant, third quadrant. So it will travel in second and third quadrant, and it goes like this somehow. And at high frequencies, this magnitude becomes very small. means it go to origin, okay, and phase is minus 270, that means this curve slide on this positive imaginary axis, okay. So this information known, then you smoothly connect this like this, then this is the polar plot of this frequency response characteristics, okay. So the same thing shown in different format, okay. So this part goes to there, this part goes to this, and this part goes to there, okay. Suppose this one at one frequency, this at omega d frequency, magnitude is larger than 1, and phase is minus 150. So phase, that frequency might be here, that this angle is minus 150 degree, and the magnitude is, we don't know exact value, but it is larger than 1. This is 0 dB. So if you draw the unit circle, somewhere here, unit circle, the radius of unit circle is 1, okay. So maybe this is this point, omega d point, because this radius is phase is minus 180 degree, and the radius is larger than unit d, so it's outside of the unit circle, so maybe this point, okay. You don't know which frequency at each point, because there is no information. The information about the frequency is hidden here. At some particular frequency, you can figure that out, but in general, it's not shown, okay. But you know this is outside of this unit circle because it is above this 0 dB line, okay. And maybe at this point, omega c point, phase, assume this is minus 180 degree, okay. That means phase is minus 180 degree. That means this polar plot is minus real axis, okay. Minus 180 degree is negative real number. It's somewhere here, so, okay. So at this point, it is on this line, and the magnitude is just 1, okay. That is what? That is this point, okay. Is on the unit circle, and this point should be 1 point, minus 1, 0 point, okay. Then what is the case? At this frequency, phase is minus 180 degree, and the magnitude is 1. Then system is what? Marginally stable system, okay. Then this, if it happens like this system is on the boundary of between stability and instability. That is called the marginally stable system, okay. You understand this, okay. This is simple but important to understand this, okay. So for this case, because of this fact, this is marginally stable case, okay. Then stability assessment is very, very simple, okay. When phase becomes minus 180 degree, okay, then means this polar plot cross this minus real axis, magnitude of that at that point is smaller than 1, system is stable. That magnitude of that point is exactly 1, then this passes this minus 1, 0 line, then is marginally stable, and at that frequency, when phase is minus 180, magnitude of polar plot is larger than 1, it goes this part, okay. Then phase is minus 180 degree, that becomes minus real number, so it should pass this line, okay. If it passes this line segment A, then magnitude is smaller than 1, that means that the ratio is reducing. If it passes this point exactly, then ratio remains 1, so sustained oscillation is going on. if it passes this one, ratio, okay, ratio between excitation and the return is larger than 1, that means is growing oscillation is coming up. Okay? So that means when polar plot is passing minus real axis at line segment A, system is stable. If it passes this point B, system is marginally stable. It passes the line segment C, system is unstable. Okay? That is the same as you understand the Nyquist analysis. Nyquist analysis is saying is this polar plot is encircling. This is unstable. It's not encircling stable. It passes this point, is marginally stable. It's the same information. Okay? So this the analysis we have done in very primitive way in the sophomore level. Okay, that is the simplest case of Nyquist analysis, but that is the sufficient for most applications. Okay, something strange you can come up with, you can make some strange things, but that won't happen in practice in this converter. In this converter, mostly this type of this occurs. Okay, all the trajectory is homing to this origin because we should have integrator for the DC regulation. If there is an integration, okay, at high frequency magnitude becomes infinitely small, then all this trajectory should come here at high frequencies. Okay. So you can read this, or you don't have to read this. Just understand this and remind the Nyquist analysis is the same thing. The simplest case of Nyquist analysis. Okay. Here is a specific example. So line A, trajectory A, trajectory B, trajectory C. It passes. This is line segment A, so it's stable. So it shows this decay oscillation with this. Okay, magnitude evaluate at this frequency. This frequency is where the phase becomes minus 180 degree, this one, and that damped oscillation occurs at this frequency. Okay. In this case, this remains the same. It becomes unity, then sustained oscillation will occur at this frequency. If it passes this, okay, it becomes unstable, and the growing oscillation is coming up, and oscillation frequency is this one. Okay, assume they are packed together, so the distance becomes small. Then maybe you can consider all the oscillation occurs at this frequency approximately. Okay, but this is okay. This is still okay. All right. This is actually the exact duplication of Nyquist analysis. Okay, encircling, not encircling. It's the same information. All right. Then we have these cases. Okay. So this is a stable case, not encircling this or passing through line segment A, encircling this or passing through line segment C, and this is it's passing this critical point. It's marginally stable system. Okay, this is what? This is the result of Nyquist analysis for the simplest case. Nyquist theory is very big. Okay, the final conclusion is they are using almost always this simple example. Okay, so we use some other approach and we reach it at the same conclusion here. Okay, and sometimes people prefer using this Bode plot. Okay, so originally maybe stability is determined this polar plot, but people they think this is difficult and this is easy, so they prefer to use this Bode plot format, or the simulator, circuit simulator, PC or simplest, and the measurement provide this. Impedance analyzer provide this. You have this plot. You need to take the low data and you do some very simple program to change this polar plot form. Or some software has that kind of built-in feature, simple program, but usually this is the easy to see. Okay, so let's determine the stability of a system using this. Okay. So criterion to be used is when phase becomes minus 180 degree. If there is no frequency of this one, then system is stable. You don't have to worry about that. If there exists one frequency where frequency falls to this value, then take a look at magnitude. So magnitude is below 0 dB. That means what? This length is smaller than 1. That system is stable. Okay. Take a look at this. So at this point, phase is minus 180 degree, and this is positive value. That means magnitude is larger than 1, means it passes this side. Okay. Line segment C is a stable one. And this is what? It passes here. Then this is the marginally stable system. Okay. So it's the same information, but somehow students, engineers, and myself prefer this one. The original definition, Nyquist is coming, this plot. We start from the something else, but we reach the same conclusion with theirs. Okay. All right. Oh, okay. This is very important. This is stable case, unstable case, and this is marginally stable case. There is another strange case. So it behaves something like this. Okay. So it does not encircle this point. Okay. Oh, in our criterion, it passes the line segment to C twice. Okay. It's something confusing, but forget about that. Okay. Think about Nyquist. Nyquist, this guy is avoiding encircling this, so this is stable. This is stable, but it is a very strange system, or very eccentric system, or very bad system, phony system. So there is a special name on this conditionally stable system. What is conditionally? What kind of condition? This time it is stable, but somehow the integrator gain, the feedback gain is decreased. The smaller feedback gain implies contraction of this thing, this curve. Okay? Somehow this curve is contracted like this with something. Then this is encircling. This one becomes unstable. Okay? So it is stable at given condition, but it can become unstable very easily. Okay? We'll come back at this point in Thursday. Okay? And I have some story about this, very important story about this. The conclusion is this one is worse than this one. Worse than this one. Okay? This is the worst case. This is the worst case. Okay? Okay. All right. Okay. That's it for today. Okay. Thank you for your attention. And